Hello everyone, my name is Paranjay Sharma. I am a student at IIPS DAVV. This video is regarding about my assignment for the subject Introduction to Data Science. I am in currently my fifth sem of MCA. We are in a playlist for the end semester examination solutions. So we are on the question number third as of now. You can refer previous videos for previous videos in the playlist for previous questions and solutions. So let's begin. So the question number 3 A part asks us to do the explanation of data wrangling process with a suitable example. So data wrangling is basically the process of cleaning, structuring and enriching raw data into desired format for better decision making. It has 6 core steps: discover, structure, clean, enrich, validate, publish. For a real example or a real life example, we take a scenario of e-commerce sale. In this we have raw data, then we categorize the field data, then the prices are converted to float, then the cleaning and its cleaning is done. It's now ready for analysis, and that's all. It's done now. We can publish it as well. So these were the 6 steps. Discover. In discover we understand what the data we have. In structuring we normalize the format, example reshape, scaling, etc. We clean, we fix null values, errors, duplicates, nan handling, etc. Enriching, we add new features or attributes in the data to make it more informative. Then we validate it against various rules. If it is verified against rules, then it's validated and it's ready for publishing. That is the output we have. We can use it for analysis as well. Then coming on to the next part of the same question number 3, it asks for difference between errors and artifacts in data cleaning and explaining any two imputation techniques. So basically, first we will distinguish between errors and artifacts. Errors are basically incorrect values caused by unpredictable mistakes during data collection or entry. Example can be human typos or sensor glitches, transmission packet loss. In artifacts, these are basically the systematic noise, the distortions that result from processing method or equipment itself. These often looking like valid data. So its origin can be compression algorithms, equipment limitations, specific software defaults. The nature for errors can be random and unsystematic, whereas for artifacts it can be systematic and reproducible. So we can control it. We can control the artifacts in the data science field. Then for example, we have a human age record as 200 instead of 20. In artifact, a digital image having blocky edges due to compression. Then we have the next part, which is about talking about imputation techniques. So the common imputation techniques are mean median imputation, which we talked about in earlier videos as well. We take the mean and replace it with the missing values or zero values. It's simple to implement, but it reduces variance, which assumes missing data is similar to the average while it is not in real time. The second technique is last observation carried forward, that is forward fill. It reflects the state of reality, but the cons are it can propagate errors if the last value was an outlier. So that's all about imputation techniques. Now moving on to the question number 4. In this we have to explain 4 common feature engineering techniques for continuous or categorical data. For categorical data, we can use one-hot encoding and label encoding. One-hot encoding is basically it creates a new binary column 0 and 1 for each unique category. In label encoding, we assign a unique integer to each category. So, used when it is used when data is nominal, where that is no order, like color, red, blue, or city. It avoids implying a false ranking. It Whereas label encoding is used when data is ordinal, that is, it has order, like size, small, uh, like size, small, medium, large. The order can be between 0, 1, 2. It makes sense, right? Then we have continuous data techniques. In continuous data techniques, we have min-max scaling, binning. We have already discussed these two before, but we can always revise it. So the concept is rescales data between 0 and 1. It's min-max scaling, and whereas in binning, it converts continuous numbers into discrete intervals, that is bins. Then coming on to the next part of the same question number 4, we are given a data set. We are asked to compute mean, median, mode, and standard deviation, and explaining about the formula for the data set is this. So for the mean, what we do is basically we take the summation of all these values and divide it by the total number of values. Median is the middle value, which is calculated here in this case. We have odd numbers, so it will be n plus 1 by 2, and that will be the middle value, which will be 15. First we order it, then we will get 15 as a middle value. The most frequent values are 12 and 15, so it will be a bimodal type of data set. And the standard deviation, we can calculate it by the formula of square root of summation of x minus x bar whole square. So that's about this question. Moving on to the next question. In this we will this is the question number 5, in which we have to distinguish between parametric and non-parametric models and supervised and unsupervised learning. In parametric models, these are basically the models with a fixed number of parameters uh, which are independent of number of training examples. They make strong assumptions about the data, like it's a straight line, but its cons are it cannot learn complex patterns, which is resulting in underfitting. Its famous examples are linear regression, Naive Bayes theorem, etc. Non-parametric models like KNN, decision trees, support vector machines, they are highly flexible, and the number of parameters grow with the amount of data. So they make fewer assumptions and let the data determine the structure. But it's slower, it requires more data, and there is a risk of overfitting as well. Coming on to the fifth questions part B. With reference to text mining, we have to describe accuracy, precision, recall, F1 score, and illustrate their computation using a confusion matrix. So the confusion matrix contains true positive, true negative, false positive, false negative. True positive is basically the correctly predicted uh, positive. It's true negative is basically the same as correctly predicted negative. False positive is type 1 error, and false negative is type 2 error. So the metric definitions are basically uh, for accuracy we have true positive plus true negative divided by summation of all the metrics from confusion matrix. Then we have precision, which is exactness. It tells us about out of all items labeled positive, how many are actually positive. Okay, so this is the formula for that. In recall, we check out of all the actual positive items, how many did the model find. In F1 score, we get the harmonic mean of